to this special prestige event organised by the Southwest branch of the IOP in collaboration with the Atlas experiment at CERN. I won't say good morning, won't say good afternoon, as I know we have audience members not only from the IOP in the UK, but also from North and South America. My name is Connie Potter. I work at CERN for both the Atlas experiment and CERN Outreach. Today's event is kind of in three parts. The first was to watch the beautiful film, A Day with Particles, which I hope you all enjoyed. Then we're going live 100 meters underground to the Atlas experiment and two terrific Atlas physicists. And finally, you'll have the chance to put what you've picked up to good use when you join in the quiz, where the winner will get a prize bag of Atlas merchandise sent by me. So now it gives me great pleasure to hand the screen over to your host for today, South Central IOP branch chair and physicist fusion researcher, the brilliant Dr. Chantal Nobbs. Chantal, over to you in the UK.
Wonderful. Thanks, Connie, for that introduction. And of course, thanks everyone for joining us on both Zoom and on YouTube live as well. So we've got a really great program lined up for you today as part of the Prestige IOP event. And today's event, as Connie said, has been organised jointly by the Institute of Physics South Central branch that I'm representing today as the South Central chair, and Elizabeth Cunningham as the South Central secretary, and was co-organised with the Southwest branch. And we have the chair of the Southwest branch with us, Vince Smith, and the regional manager, Miranda Addy, joining us as well. And bridging both branches, we also have the brilliant Anna Wall, who is our branch support coordinator for both the Southwest and South Central. And Anna will be helping us with all the behind the scenes technical support today. So if you have any technical issues at all during today's event, please drop a comment in the chat, and Anna and Miranda as well are on hand to help wherever possible. I would also like to introduce Stephen Bostock, who will be providing BSL interpretation throughout this evening's event. And finally, I'm absolutely thrilled to introduce our fabulous hosts over at CERN, who are ready and waiting to take us on an exciting tour underground. So we have Dr. Clara Nellist, a particle physicist working for Radboud University and NICF in the Netherlands at the Atlas experiment at CERN. Clara has worked on upgrades on the pixel detector, studied the Higgs boson and top quark, and is applying machine learning algorithms to search for hints of dark matter in the data. And Dr. Mohammed Alhroob is a postdoctoral fellow at the University of Oklahoma in the USA and a member of the Atlas experiment since 2006. He has searched for the rare top quark production processes and is participating in the Atlas pixel detector activities. So the running order for today's event will be the tour with a short comfort break partway through, followed by a quiz at the end with some Atlas and CERN goodie bag up for grabs. So please do stick around for the quiz following the tour. But without further ado, it's my great pleasure to hand over to Clara, who will kick off our tour starting above ground before we head below ground to take a look at the experiments. So thank you very much, Clara. I will hand over to you.
So thank you, Chantal, and thank you, Connie, also for the introduction. So yeah, as you can see, I am above ground and it is beautifully sunny here in Switzerland. So I'm currently near Geneva. So I'm on the border between France and Switzerland. And I am standing directly above the Atlas detector right now. But first I wanted to show you how we get underground. And before I do that, I'm just going to turn my... Let's turn my camera around. So we have this beautiful mural outside the Atlas detector, and it helps to give a good description of what you're going to see when we go underground. So I'm above the LHC and the Atlas detector. So the LHC is a 27-kilometer long tunnel with a particle accelerator, and we accelerate protons and sometimes ions to very nearly the speed of light and then collide them in the center of detectors. And these detectors you can think of like giant particle cameras. And this mural here, I'm trying to hold my camera steady. gives you a good idea of what those detectors look like. So we have, you can think of it a bit like an onion. So we have different sections. Oh, can you hear me?
Yep, we can hear you, Clara.
Okay, excellent. So we have different sections, and they each do different jobs within the detector. So essentially, we break it down into three parts. So we have the center of the detector, which is the tracking detector, and it tracks charged particles as they pass through from the center of the collision outwards towards the edge. And you can see those white lines in the center of the detector. Then we have a section called the calorimeter, and this measures the energy of particles as they pass through. And then on the outside, we have these beautiful muon wheels, which you will see directly in a moment. And muons are the heavier cousins of electrons, and they travel all the way out to the edge of our detector before they're measured. So this image gives you a good idea of what you're going to see when we get underground, because the detector is so huge that we can't see all of it at once. We have to show you it in parts. Now I'm going to turn my camera back around so you can see me. And this is the most sunshine I've seen in almost a year. So I'm going to get inside and head underground. So I head on this way. Oh, and the first thing I have to do is put on my mask. So we have a lot of safety equipment that's required, not only for the current situation, but in general to ensure that everybody is safe when we're heading underground. So I also have my hard hat. Doesn't want to go on. Okay. And then I'm going to leave you in a moment, but just to show you, if anyone has seen Angels and Demons, then you may have noticed that there was a scene in that film where they had to use an iris scanner to access the underground area. Now, a lot of that film is not true. Obviously, it's fiction, and we can talk about anything that you heard about in that film and you want to ask questions about. But this part is actually correct. So we do have to scan our irises to get underground. So now I'm going to head through these first set of green doors, get my iris scanned, and then head down the lift. But while I'm doing that, I'm going to hand over to Mohammed, who is already underground, and he's going to show you the detector from there.
Hello, Mohammed.
Hello. Okay, hello everybody. So I am almost 90 meters underground. So I came earlier before Clara. And I am on side C. So we have two sides, A, B, actually three, A, B, C. The end caps A and C. I am on side C and looking at the muon spectrometer. So the big wheel, and if you look carefully in the center, you see the LHC. So that's the LHC line, the blue line. It's a huge, and just to give you an idea, so if you look, you see the shaft, which is maybe 60 meters long, the shaft, but then we have the cavern. And the detector is so huge. So we have, as Clara said, we have multi-layer structure. So we have the tracking detector, we have the calorimeters, we have magnets, we have the solenoid magnets, which is extremely strong, envelopes the tracking detector. We have 8 toroid magnets. They produce a magnetic field between 2 and 6 Tesla. Actually, Atlas is named after them. So it's a toroidal LHC operators. And finally, we have the muon spectrometer, which we see right now. So this one, we call it the big wheel. It's a huge, it's around 27 meters in diameter. And the idea is to track the muon particles, the heavy brothers of electrons. Here, if you look carefully in the center, we have something, we call it the small wheel. It's a muon spectrometer. We call it small because it's small compared to the big one, but in fact, it's very huge. And of course, Atlas is very heavy detector. It's around 7,000 tons, equal to the Eiffel Tower in Paris. And we have lots of infrastructure, lots of supporting structure. So you can see this scaffold around 100 tons. They lower it because we have a long shutdown. We have to move the detector parts. We have to carry them because the detector somehow is dismantled. And when we push the Muon spectrometer to the center or move it, this scaffold should be removed upstairs. Right now, it's not running the detector. Otherwise, I can't be here because we will have lots of stray radiations. But since we have the long shutdown, which we need every 4 years for maintenance, we don't have radiation, and technicians, operators, guides like me, we can come underground. Maybe I can move a little bit to show you the toroid magnets. So if you look at the blue the tubes with orange strips, those are the toroid magnets. We have 8 toroid magnets. As I said, they produce a magnetic field between 2 and 6 Tesla, which is a huge magnetic field. It's like 60,000 times stronger than the Earth magnetic field. They are superconducting magnets because the cables, not copper cables inside, they are made from titanium niobium alloy. And to achieve the superconductivity, we have to cool them down to minus 271 degrees centigrade. That's the temperature where the where the magnets or we achieve the superconductivity. Now, maybe if you look carefully inside there, we have the hadronic calorimeter, but it's very actually it's covered by scaffolds right now. We have 2 calorimeters. The first one, we call it the liquid argon calorimeter, which measures the energy of electrons, positrons, the antimatter of electrons and photons. It comes immediately after the solenoid magnet, which surrounds, envelopes the tracking detector. The second calorimeter is the hadronic calorimeter, which measures the energy of hadrons. Hadrons is a family of particles, composite particles made from quarks and gluons, like protons and the neutrons. Now, if we measure the tracks of charged particles like electrons and muons, so we can measure their energies and their momentum. Sorry, their electric charges and their momentum. Calorimeters provide energy. So if we have the energy, the momentum, and the charges, we can calculate the masses and we can identify particles. So we know this particle or track caused by an electron or positron or muon or other particles. Of course, since we want to make discoveries, we need very precise measurements. And although the detector is very huge, we need to know each sensor up to a micrometer level. And that, of course, involves lots of technology. We need laser to measure the distances. We need lots of alignments. We need to control the temperature because, you know, material expands or contracts by changing temperature. And if we want to achieve micro level accuracy and we allow the temperature to fluctuate, then, of course, our detector becomes blind, or we become blind. Different subdetectors work at different temperature. For example, the innermost part of the detector, the pixel detector, it's the most precise detector. It's like the digital camera which we have in our mobiles. We have 92 megapixels organized in 4 concentric cylindrical shells, and it's a 3D camera actually. And we can take 40 million frames per second because that's the rate of the collisions at Atlas experiment. 40 million collisions per second. This pixel detector runs at extremely low temperature. So the innermost layer, it runs at minus 80 degrees centigrade, and we use carbon dioxide to cool it down. The other pixel layers, as I said, we have 4. They run at minus 60, 20, depends on the high voltage we use. And so we need to use fluorocarbon C3F8. Since we have sub-zero temperature also, it's very important to control the humidity. So we flush the detector by dry air. If we allow humidity to stay in the air, and we have sub-zero temperature, we form ice and we can damage the detector. As I said, magnets run at extremely low temperature. We use super liquid helium, and the temperature is minus 270 degrees centigrade. Calorimeters varies. For example, the liquid argon calorimeter runs at minus 183 degrees centigrade because we use liquid argon. The other one runs at higher temperature. The muon spectrometers run at room temperature, and actually the technology is old. We don't need very precise detectors. It's unlike the pixel detector. Since it's very far away from the collision point, so when we make the tracks, even if we have plus minus 1 centimeter as an accuracy or uncertainty, we can achieve very good angle measurements. I want to say the detector is huge. It's very heavy, it's very complex, and we need to know every sub-detector again up to micrometer level. Right now, as I said, we don't collide. We have 2 years shut down, and because of the pandemic, it's almost 3 years. This this small wheel will be removed. This is an old one, and right now they are assembling 2 new small wheels upstairs. They will install them hopefully this year, because at the end of the year, I mean, we will have the LC running. So if we don't install them, we will miss the opportunity to improve the accuracy of our detector.
Mohammed, just to let you know, I'm back. So I just took the lift underground, which is why I used internet, and we did that bit separately. So now I've also climbed up 12 flights of stairs. So I took the lift almost 100 meters underground, and I've now just climbed up 12 flights of stairs because I also want to show you a really special view of Atlas. So I don't know if you still have more you wanted to say here, Mohammed, or?
No, you can show us Atlas from the top, which is, I mean, which I can't see from here.
Exactly. So Mohammed is now on the second floor, and he's you can't see that yet, but he's sort of that way on the other side of the cabin. So we've gone to separate places within the cabin because we want to show you different views. And if we didn't have the pandemic, then we would welcome visitors to Atlas during the shutdown period. So normally people can come underground, but the place that I'm stood right now is a place that even visitors don't get to see from. So unfortunately, you can't be here in person, but you can get to see this extra special view. So I'm going to turn my camera around again. And so right now I'm in the cabin, and where I came from is from right up there. So you can see a bit of the sunlight from the roof coming through. So that's where I was a moment ago on the top, and I've come all the way down, and now I am standing directly above the Atlas detector. So here you can see it from above, and if you look very carefully, oh, where did he go? Oh, yes. If you look very carefully down here, there is somebody currently working on the detector. So as Mohammed has been telling you, we've been shut down and we're performing upgrades and repairs during this period. And so this really is an active work site. It's a scientific workplace where we're performing all of these upgrades and repairs. So what you might ask, looking at just how huge the Atlas detector is and how much space we have within this cabin, you might ask, how did we build something this big in this space? Well, if you've ever seen anyone build a ship in a bottle or that kind of hobby, it's exactly the same technique. So what we do is people, scientists, engineers, technicians all over the world, they are constructing different parts of the detector. And when they're close to completion, they get sent to CERN, they get built into bigger components, and then these parts get lowered piece by piece from this shaft, and there's 2 other shafts in this cavern, down into the cavern and then constructed in place. So we take pieces out. So Mohammed was just telling you about that muon wheel that's going to be replaced by a new one that we're constructing. So that in itself is small enough that it can fit directly up through the shaft. So when we want to replace it, we're going to take the whole thing, lift it up, and replace the new one and slot it in where it needs to go. So that's how you build a machine of this size in the cavern and use up really as much of the space as possible.
Clara.
Yeah.
Hi, is it okay if I come in with a question just quickly, just while you're talking about building Atlas?
Yeah, absolutely.
So we have a question that says, how many nations are or were involved in the building of Atlas?
So this is a great question. So if you're talking about the number of countries that are actually a member of Atlas. So yeah, somebody just said, I thought Lego was difficult. This is like a huge Lego project. Yeah, so Mohammed can maybe confirm the number, but I think it's about 38 now countries that are members directly of Atlas. But
yeah, that's a true number, yes.
Yeah, perfect. But we have over 100 people from over 100 different countries working on the experiment, because not everybody comes to work at institutes where they're originally from. It's such an international environment. It's a really international collaboration, and we have people from almost every planet and definitely from every continent in the world working on this experiment. And yeah, it's truly a global endeavor to work on it. So I saw another question, which I'm happy to also answer. So the question was, is Atlas the largest detector? And it is. So there are 4 major detectors on the LHC. So we have Atlas and we have CMS. We also have LHCb and ALICE. And Atlas is the biggest, and it's partly because of the size of the cavern that we had available. So there is some sort of construction constraints that we have when deciding how big the detectors are. And our sibling detector, you can think of CMS, which is on exactly the opposite side of the ring, actually has compact in its name. So if you saw it, you wouldn't think it was very small, but it does have to be more compact than Atlas is, just because of the size of the cavern that was available to the team that was working there. So yeah, Atlas is the biggest one. Partly also that motivates the name, that it's named after a Titan from Greek mythology.
Great, thanks, Clara. Yeah, do carry on, and we'll come back to some more questions in a bit.
Excellent. Yeah, so I'll just let's have another look from this angle. And what I really want to show you, with of course not dropping my camera, I have it carefully tied up on the barrier here. So what I'm directly above is, you can see from Mohammed's camera those muon wheels, the large muon wheels, and I am actually directly above the other one. So on the other side of the detector, you can now see it from above as a sort of cross section. And this is the outer edge of the Atlas detector. And then you can see, for example, this scaffolding that's down there that you'll see from another angle in a moment when I head down alongside the detector, but from a higher vantage point than Mohammed's at. And this is so that we can access all the parts to do the repairs and construction right now.
Clara, sorry to interrupt you again.
Yeah.
So just while you've got that really nice view, and maybe maybe when I ask the question, maybe you'll want to wait for a different view to help answer it. The questions come in that says, please indicate the line of the beam and the direction that the particles can travel in.
Yeah, so that's a great question. So I'm almost directly above it. I could move a bit further to the left and I'd be directly above the LHC beam. But if you see where my hand is pointing, then this is the direction that the LHC beam would travel in. And it goes in both directions. So we have 2 beams in the LHC, and they circulate in opposite directions. And in the center of the Atlas detector, which is over here, somewhat over there. So if you remember when we started, when I was above ground, in the middle of the mural, there was the center of the tracking detector, and those lines that come from it is the center of the collision. Well, that happens over here in the center of the Atlas detector, but we can't get to that point right now, because it's really, we would have to go crawling around inside the detector, which is not possible from here. So the LHC beam travels this way. And we have, so there are magnets that control the beam as it travels. So there are lots of different types of magnets that the LHC accelerator physicists use to control the beam. And that's really a whole separate team of people who are experts on making the LHC work and improving it and studying accelerator physics, which is a really important field also for applications outside of CERN. So accelerators can be used in medical hospitals for cancer therapy. So it's not exactly the same accelerator that we have here. You don't super cool the magnets for those. But what we learn here really can be applied in other places. And you can take the same kind of physics, shrink it down, and use the particles that we're using here to treat cancer. So there's a lot of connection between the work that we're doing and the work that happens in hospitals. Yeah, so the LHC has these magnets, and there are different types. You have dipoles, which control the bending of the protons as they go around the ring. And then we also have what are called higher order magnets. So we have quadrupoles, sextupoles, octupoles, and these higher order magnets then control the focusing of the beam. So we want to get those protons nice and compact. And we also, as they get really highly energetic, they can tend to sometimes misbehave a bit as they're traveling around the ring because they become what's called chaotic. And so we have these higher order magnets that really control where they're going, and they do exactly what the accelerator physicists tell them to do. And this ensures that the collisions that we have in the center of the detector for people like me and Mohammed, who are particle physicists, that we get the most collisions possible, and that we really know, we want to know what's colliding, what energy it's colliding at roughly. It's difficult with hadrons. And we want to get as many collisions as possible so we can collect as much data so we can study the particles that come from those collisions. So Mohammed, I don't know how much you talked about the actual different things that we're studying with the collisions, because I didn't get to hear you while I was going down the list.
I did not mention the physics we do, but of course we have 20 billion collisions recorded, and take into account that we record tiny fraction of the collisions occur at the center of the detector. Actually, we delete 99.99% of the collisions because they are caused by non-physics, elastic collisions. The fraction we keep is ended, run with the 20 billion collisions. We study so many things. We study the topic quark, the heaviest particle, which me and Clara work on. It's very interesting because in new physics, in new models, predict particles that decay into topic quark. Of course, in order to make discovery, we want to understand, measure the parameters, the standard model parameters very well, because the discovery is made by looking at observation and deviation, by measuring the deviation from the known theories. We study, of course, standard model processes like W boson, the production of W boson, Z boson, and other known processes already discovered, but we want to measure them with high precision. Of course, we have searches. We have SUSY, supersymmetric particle searches. We have exotic models. We want to understand how many quarks in nature we have. We know 6, but do we have more? How many leptons? Why we have 3 families of quarks and leptons? How many bosons? How many fundamental interactions we have? Of course, how many dimensions in nature? We live in 3 spatial dimensions. Do we have more? Logically, it's possible. And there are many theories that predict that in order to answer many open questions in physics. We are 3,000 physicists in Atlas. Of course, if you add students and engineers and contractors, we are maybe 5,000, 5,500. The 3,000 physicists are divided into major physics groups. Like we have SUSY, the supersymmetric group. We have the Higgs boson, the known particle or the God's particle. We have the exotic group. We have the B physics. B means B hadron. It's a composite particle discovered long time ago, but it's very interesting because it decays via weak interaction. We have the top, and each group has subgroups, and each subgroup focus on one particular aspect of a particle or a process. we have so many things, we have so much data to explore.
Yeah, so just to add it, yeah, as Mohammed was saying, we have so many collisions. So we have 1 billion collisions per second from the LHC, which is just an incredible amount. And as Mohammed was saying, we can't keep them all. So we can only keep about 1 million of those at a time. So you get 1 billion collisions per second, and we can only keep 1 million of those. And so we have these selection criteria. So people in the Atlas experiment are trying to work out what is interesting, what we want to keep. So all of these different study groups that Mohammed was talking about, we then have to decide how to keep that data. So it's a very special part of the analysis we're doing, is just to make sure we're not even throwing away the interesting stuff. And just to be extra careful, we do have one set of data that is just a random collection. So in case somebody comes along later and has a really clever idea and it's like, oh, why didn't we think that we could look for the particles in this way? Then we look first in this random stream of data to see whether or not we threw that data away.
So yeah. Can I add one thing, Clara?
Yeah,
so
absolutely.
You mentioned 1 million. So the trigger system is made from 2 levels. Level 1, which is decided by the trigger itself. We keep 1 million. The 1 million collisions, we call them the trigger candidates. We send them to a cluster of computers. We run the software and we reduce the rate to 1,000 collisions. So out of 40 million, we end with 1,000 collisions permanently recorded. So 2 levels, and it's very tricky because you want to maximize the efficiency, the signal, we call it efficiency, and to reduce the fake rates as much as possible. And so we need to understand the detector, we need to understand the physics we are searching for, because we want to trigger the collisions according to the signatures we know.
Yeah, and as you were saying with all these different groups, so a lot of people think that the Atlas experiment is one experiment, the CMF experiment is another experiment, but in reality, it's thousands of experiments done by even more thousands of scientists working on the same equipment. And so when we're trying to select this data, then everybody wants their data to be collected, and there's only so much we can collect. So we have to be very careful how we're making these decisions. So I think I'm going to head down to the 6th level now. So I'm going to give you one last look from up here. This is really my favorite view of the Atlas detector from up here, because you really get a sense of the size. So it goes all the way back to the other end of this cavern. And here you can really see the size of the detector. So I'm not sure if we said before, but it is it's about 25 meters across, and it's 46 meters long. So it really is a huge detector down here. And it's interesting. I mean, a lot of people ask, like, why do you need such a huge detector for something so small when we're just trying to measure these tiny particles? But because they're so energetic and you want to stop them whilst accurately measuring their properties, that's why we need such a big detector, to make sure that our measurements are as accurate as possible, so we can discover new particles, like we discovered the Higgs boson in 2012, which was the most recent fundamental particle to be discovered here at CERN. So also, just before I go, you can see there's some people down there doing some construction work. So they also give you a good idea of the size of the detector by having somebody to compare it to. Okay, over to you, Mohammed. I'm going to go for a walk.
Okay, Clara, I'm going to walk toward side C, and I show you them how we walk. I mean, it's again 50 meters long, just to have a perspective of the size of the detector. As you see, we have so many pipes, tubes. For example, this one is the antenna for mobiles. We have lots of couplings for cooling, ventilation, for power cables for communication, or to transfer cables to transfer data, etc. So I was in side C, and I am almost inside A, and Clara is somewhere there.
Yeah, I don't think you can see you.
No, I can't see you, but at some point she will be on 6th floor. So this is side side A. As you see, this is the blue tube is the LHC. Of course, it has to be connected at some point. This is the big wheel. It's a immune spectrometer, but it has two side one where we have the drift tubes. It works like a tracking. This one is the timing detector. It's extremely important to time the collisions because
Go ahead.
Every 25 nanoseconds, we have a collision. And the new particles, they travel with the speed of light, but before they arrive the immune spectrometer, the next collisions occur. So it's very important to associate the particles to their collisions or bunch crossing.
Yeah, so Mohammed, since you mentioned the drift tubes, I want to give people a really close-up view. So this is, I'm not gonna, but you could really touch the detector from here. We can get so close to it. And here you can see those drift tubes. So these are a tube with a gas inside and a wire. And when a charged particle passes through, specifically a muon, they release electrons in that cloud, in the gas inside of it, that's then attracted to the wire and read off. And the time it takes, which is why it's called a drift tube, the time it takes to get from wherever the muon was to where it's measured out tells us where it was within the tube and gives us a relatively accurate position measurement of the muons on the outside. So here you can really see up close to the detector and all of this beautiful cable management. Nice and tidy, like we like to see. All right, I'm going to keep going and head down to the 6th floor.
I mentioned the toroid magnets. And as I said, we have 8 toroid magnets, but those are the central magnets. We have 2 end cap toroid magnets, and this is one of them. It's a huge built at NICAF where Clara works. So they pushed it away in order to have access to the detector. So at some point they have to pull back the toroid magnet and they connect the LHC. And of course, before that, yeah, go ahead.
Did we tell people why we need magnets? Why do we have magnets in the detector?
No, I didn't tell them. So go ahead.
That's very important. Okay, so we have magnets in the detector because, as I was just saying, we want to measure the properties of all of the particles as accurately as possible. And one of the properties we're really keen on measuring is the charge of those particles. And magnets bend charged particles as they travel through the magnetic field. And so depending on whether they bend one direction or the other, it tells us if it was a positively charged particle or a negatively charged particle. The other thing we can get from the measurement of how much it bends is it tells us something about that particle's momentum. And so that can also help us to identify what kind of particle it was as it was traveling through. Was it an electron or a muon or a proton? So we can get a lot of information by having those magnets in. And one more thing since I'm here, because we had that nice question about the LHC beam direction. So I'm currently inside, underneath where I was, and right next to the detector, not quite inside the detector. And what I can show you is this blue section here right underneath my feet is the LHC beam pipe. So I'm currently standing directly above the LHC. And if I was a proton, I would be going this way or that way into the center of the detector or away from the collision. So right now I'm right above the detector and I'm crossing over. I'm going to go over to the side of the detector this way. And again, you can see these drift tubes really close and just how many of them we have to make sure we measure all of the muons getting to the outside of the detector.
So maybe I can see you now.
Are you looking up? Let's have a look.
Yes.
We'll wave at each other.
So I am on the floor, on the second floor. You see Clara walking.
There we go. Hello. So now you get a sense of where each of us is. So there's Mohammed. And so now I'm standing next to the side of the detector. So you get a more side-on view. So where I was a moment ago, to help give you perspective. So I was up there on that top platform looking down onto the detector, and I've come down and now I'm standing next to these muon wheels. And then here is the calorimeter section with those magnets.
So I'm going back to side C and keep going, Clara.
Well, I know that one of your favorite facts, Mohammed, is about the temperature of the LHC. Do you want to tell people about that, or have you already done it?
I told them. So
Excellent.
I told them that we have so many sub-detectors and some of them run at extremely low temperature.
But what about the LHC itself?
The LHC runs like at the same temperature as the Atlas magnet, so it's minus 271 degrees centigrade.
Okay, and did you say specifically that it is colder than outer space? It's very,
yes, it's
very, very cold.
1.9 Kelvin. So
yeah,
the average temperature is 2.7 Kelvin. And the LHC magnets or the Atlas magnets, they run at 1.9 Kelvin. So I can claim that the LHC and the Atlas magnets are the coldest place in the universe at industrial scale.
That's a good point, because there was also, I mean, atoms have been cooled to a lower temperature, but those are just individual atoms. So
yeah.
Yeah.
And the amount of helium we have at CERN is around 120 tons, half of the world's consumption.
Yeah. So I think, Chantal, did you have a question for us?
We've got a lot of questions
Excellent.
coming in, absolutely inundated with questions, which is brilliant. I'll throw a couple at you. How much more of the tour after this have you got left? How many questions? Should we just get through a few now?
So Mohammed and I are in place, and we can either answer questions or keep telling you our favorite facts. So happy to do either.
Okay, so let's rattle through a few questions.
Yeah.
So one quite good question: how is calibration possible at such a large scale? Do you have to calibrate each component individually?
That is a really excellent question. So calibration happens at many different stages. So, for example, the pixel detector that I think Mohammed was talking about as I was getting in the lift, the very first layer is something I worked on during my PhD. And I spent a lot of time calibrating individual sensors. So you can imagine if you took the sensor out of your camera, and I spent a lot of time on each one of those, really understanding how it performs depending on how much voltage we gave it, how much irradiation it got, what temperature it was at. And so we really get to know every single component to the tiniest detail. But then, of course, when you put them all together, they all start to perform slightly differently when they're in a larger set, and you try to control the environment as closely as you can, but of course, not always possible. And so then one way that we can calibrate the detectors once they're inside Atlas itself is that we can use muons coming from the atmosphere. So we have particles that collide with our atmosphere. And actually an interesting fact is that these collide at higher energies than we have at the LHC. So a lot of people ask me about safety concerns with the LHC. Well, these collisions that we're doing at the LHC are already happening in our atmosphere with particles coming from space all the time. So we know for sure that if it would have happened, it would have already happened in our atmosphere. But yeah, something that comes from these collisions are muons that rain down on us, basically. It's one of the background radiations that we have on everybody in our daily lives. And these muons, when they go through our detector, they travel in a nice, relatively straight line. And it helps us to calibrate exactly where everything is, and also to check that everything's working. So while the LHC is not running, actually a couple of weeks ago, we did some muon runs to check that everything was still performing correctly and to get ready for turning on again later this year, early next year. So it's really every single stage from the smallest piece to then when it's constructed together gets calibrated in different ways. And we want to check the lifetime of the detectors. So when I was talking about irradiating these samples, we're mimicking the conditions that they're going to have for 10 years of lifetime in the Atlas detector. And so we go and stick them in some radioactive beam or source to sort of damage them intentionally. And then we see how they perform after that kind of damage. And that's how we get to know how long they'll last in our detector. And we're always improving our detectors so that by the time we come to a new shutdown and we want to replace something, we've had 10 years of research and development to get the next piece in.
That's really wonderful. Thank you. You actually knocked a few other questions off the list on the way there, so that was perfect. So another question, what levels of radiation are there when the machine's operating, and how do scientists protect themselves?
You want to take it, Mohammed?
The amount of radiation, I don't know, but we protect physicists by preventing them from accessing to the cavern.
Yeah.
No one is allowed to be underground. Actually, we can't turn on the machine if people underground, because they use special keys to access. And of course, when they access, they have to take them, so they open the circuits, the electric circuits.
That door you saw me go through right at the beginning when I had to get my iris scan, that's also part of the safety procedure. So if the LHC was running, that door would just not let me through. It would also alert a safety officer that I was trying to go down the tunnel, and it would probably trip the LHC and turn it off, so that even if I managed to, which I wouldn't be able to, it would already be off by the time I got down there. So human safety is the utmost priority here at CERN, and we have so many both automatic and human safety features to make sure that nobody is anywhere near the LHC when it's running.
So we have to mention right now we have radiation, less radiation than above the ground, because we are protected by 100 meters of earth.
Yeah, so those muons that I was talking about, actually the rock above us helps to filter out some of those muons. As Mohammed just said, being underground, we get less of them than people on the surface do. But just to be extra super especially careful, we're both wearing our dosimeters, so Mohammed's got his on too. And this is a passive dosimeter, and it just checks how much radiation we possibly receive while we're down here. And when I hand this back, they'll stick it into a machine and it will measure it, and they'll keep track of it throughout the year to make sure that I don't go above a certain level, which also includes my background radiation. I'm wearing it above ground too when I'm at work. And if it goes above a certain level, then that's it. You can't perform any work around anything that's possibly radioactive, just to make sure. And the level that they actually set it to is something like 1 or 2 test x-rays. So it's really a very low amount in terms of what you might possibly be exposed to in other situations.
Perfect. So I'll do 2 more questions, and then maybe we'll take a sort of short 5-minute break, something like that, just to absorb all that information. It's been really, really brilliant. I've got, I would say, majority of the comments coming in, that aren't questions, are just saying how absolutely fantastic this tour is. So thank you both very much. So the next question I'll ask is, does any seismic activity affect the alignment of your detectors, and how do you compensate for that?
Do you mind if I answer, Mohammed? Because I really like this question.
Go ahead. I don't have a solid answer, but I can guess. Go ahead.
Yeah. So, I mean, the short answer in terms of the detector is no. We're in a very seismically calm area of the world, which is very fortunate. So the actual detector doesn't have to be calibrated for any seismic activity. But the LHC itself is so sensitive. As I was saying, we have all these automated systems. So we have automated security systems, but we also have automated systems for making sure that beam inside the LHC tunnel is exactly where we want it to go. So the accelerator physicists can tune this when they want to, but also the system keep it nice and in place. And one of the reasons they have this automatic setting is because the moon, so our moon in space, actually pulls on the Earth in a way that changes the radius of, or not, yeah, the radius of the LHC, but also it sort of squishes it in different directions. And this means that the beam has to be corrected, those magnets and the RF radio frequency settings for the beam have to be calibrated for the moon. So there's a really beautiful plot you can see of it's a sinusoidal, so like up and then down again, which is this correction over a day or over 6 hours, 12 hours for the movement of the moon. And when there are earthquakes around the world, they can be felt by the LHC. So in 2014, I think it was, there was a very, very large earthquake in New Zealand, which is almost exactly on the opposite side of the planet from the LHC, but it was so strong that the waves, the shock waves that traveled through the Earth, made it to Switzerland and actually shook the rock of the LHC, and these corrective settings had to kick in to keep the LHC, which was running at the time, exactly where it needed to be. And so you could see on this plot this nice slow movement to the moon, and then when the earthquake was, there was a couple of hours actually of sharp peaks of where it was moving because of the earthquake. What was that?
10 hours later. So
10 hours
when they
later,
calculated the speed of the seismic waves, it was consistent with the earthquake.
Yeah, and it's not the first one that's been measured. So it's the LHC is a very, very expensive earthquake measurement machine, but that's not its primary purpose, of course. There are other much more simple ways to measure earthquakes.
Brilliant. So we'll have one more question just before our break. We'll do a couple more after the break before we then go to the quiz. But I thought that just before this break, it might be nice to have a slightly less technical question, but still quite an interesting question, certainly, hopefully, to inspire some of the younger members that are joining us on the call. So at what point during your school or college careers, and this is a question for both you, Clara, and you, Mohammed, at what point did you decide you were going to be a physicist?
Clara, start. You are younger than me.
I don't think by that much. Okay, so I was always fascinated by science. I had my parents are also very interested in science and what's going on in the world around us. And so I had the upbringing to always ask questions and to find out what things are. But I very nearly didn't do physics because I went to a school that is a non-selective, comprehensive school that didn't have a lot of resources. And when I went there wasn't a physics teacher at my school. And so when I was selecting my A-levels, I was looking through the list and physics wasn't on there. And so I kind of just thought to myself, oh, I guess that's not going to be one of my options then. And was thinking about what else I wanted to do at A-level to then go on to university. But my mum, who's a teacher, again, fortunately, she had knowledge of the education system. She knew that I could do physics A-levels at another school if I wanted to still stay at the school I was at and just go for those lessons. So then I went to do physics at a second school just for those lessons. I really enjoyed it. I decided that I wanted to do it at university because it would be both an interesting thing to study. It would also give me a lot of opportunities. There's lots of career paths that can come from physics. So not just a scientist, but you can be a teacher. You can work in research and industry. You can work for the government. You can work in finance. There's lots of really great options. So I thought it was a good, solid thing to study that I could be interested in and gave me opportunities. And while I was at university, I was offered to do a research project on a different, so not on the LHC, but on the Tethertron, which is at Fermilab in the US, so in Chicago. And I spent a year working on the top quark studies remotely from Fermilab. And then I got to spend a couple of months in the US working on it. And I just thought it was so fantastic that I could be spending my time finding out how the universe works, being around people that also want to find out about these smallest building blocks of our universe. And I just felt really fortunate that that's something I could spend my time doing and then also sharing it with other people. So it's kind of step by step. I always wanted to do something to do with finding out about our universe. Go on.
For me, I decided to study physics after I finished the first year at the university. So I went to the Faculty of Engineering. Of course, I was forced to take 2 courses in physics, chemistry, calculus, etc. But at that time in 2001, everybody wanted to be an engineer. And as you know, I am from Palestine, we don't have industry. I didn't like it. So 1 year I was talking to myself, why do I study engineering? No, I want to be a scientist. And actually, most of the year I thought about math, but 2 weeks before I changed, I mean, the idea of being a physicist came to my mind. And so when I went to the university, I went to the Faculty of Science, I asked them, which topic you advise me, math or physics? A physicist said, oh, for sure, physics.
Of course they did.
Yes, and actually it was a matter of luck because the office of the chairman, the chairman of the Department of Math was closed. So I couldn't ask him, and so I met professors in the corridor and they were not serious or not pushy. So I ended studying physics.
And what brought you to CERN then? How did you get, what brought you to CERN after that?
That's also a matter of luck. So I was applying to do my graduate studies. I applied to so many places, and I was accepted by the International Center for Theoretical Physics in Italy to do theoretical particle physics. Now, if I was accepted in maybe material science, maybe I changed. So when I came to the ICTP, the courses were extremely tough for me. And yeah, and I said, okay, I want to be an experimentalist. They were making fun of me because it's International Center for Theoretical Physics. But luckily, while I was doing my diploma thesis, they started a new experimental group. They asked all the students to join. None of them accepted. They asked me and I accepted. And I found myself an Atlas member.
Excellent. So maybe I can add before we hand back to Chantal then, that there's also more than physicists here at CERN. So you're talking to physicists now, but we also have engineers, technicians. We have people who are experts in communication, so making sure that the work that we're doing is shared with as many people as possible. So Mohammed and I like to do this work, but there are people who really do it full time, which is very important because it's a key part of CERN's program. But we also have people who are making sure the technology that we develop at CERN is shared. We have human resources, people that make sure that all of the thousands of people that work here, everything is running smoothly for them. I'm sure I've missed many of the different, we have firefighters, so we have a firefighting department here at CERN, computer scientists. So really what I want to say is that some people think that it's only physicists working at CERN, but we're actually just a small fraction of the people that you'll find here. And there are so many different types of people working here on different projects. So maybe if you're watching and you're thinking, oh, well, I like physics, but it's not what I want to do forever, there are other opportunities to work at CERN as well and to get involved.
That's a really, really great message, Clara. Thank you. Yeah. Let's just take just 2 or 3 minutes. And I'm sure, Clara and Mohammed, you've got some sort of really spectacular backgrounds that you can show us just while we just take a couple of minutes just to look away from the screen for a bit and maybe sort of take a quick comfort break. And we will be back at, let's say, 3 minutes past the hour, so 3 minutes past 4. And we will ask a few more of the questions. So if you're thinking about your questions, get them in now. We'll try and answer as many as we can. And then at 10 past 4, we will start our quiz. So yeah, I will join you at about 3 minutes past 4. Okay, hi everyone. So we will now return for a couple of questions. I'm hoping that both Clara and Mohammed are still there. We've still got our experts on the ground. Perfect, thank you. And I can see you, Clara. Hi. So I quite like this question. I don't have any idea what the answer might be. So I will throw it out to you. Could I know why Geneva was considered as the optimal place for building the LHC? Do we know?
You want to take it, Mohammed? Or?
Go ahead.
So, I mean, it's a historical reason, and actually, maybe, I mean, if Connie might know this as well. I mean, CERN was set up in the 50s after the Second World War as a way to bring European scientists back to Europe and to have a collaboration between countries for peace. It was really set up to foster peace within the region. And Switzerland was a neutral country and was decided to be a good place to start building the first accelerator here as a neutral political country constructor. And then eventually everything got so big that we've had to also start building on the French side. And so there are a lot of discussions between France and Switzerland about how CERN works as a site.
Can I add to that, Clara?
Oh yeah, absolutely.
One of the reasons they say was that Switzerland was very central in Europe, so people from north and south, east and west could come. And also, and I think this was the main reason, there were so many other international organizations already based. I mean, the League of Nations before the war, which became the Swiss office, the European office of the United Nations, but also the World Health Organization, International Labour Office, International Telecommunications Union. You're in Geneva, so you'll know how many of them there are. And I think it was very easy to add one more international organization.
Yeah,
it's interesting to note that although we don't do nuclear research, but it's in the name because nuclear was the buzzword in the 50s. The European Council, now the European Organization for Nuclear Research. Switzerland, as you know, is very fond of having plebiscites. And so they were asked, would they welcome CERN in Geneva? And it was passed by a very large majority, over 2/3, I think, because of course the employment possibilities of having CERN in Geneva. Thanks.
Thanks, Vince. Let's see if we can squeeze at least one more, maybe two. So how much energy do you know is required to power Atlas, and does CERN use renewable energy where possible?
I know Mohammed is good at answering this question.
So Atlas experiment consumes around 1 megawatt. So not so much because we have superconducting magnet. So if you compare it with the energy consumed by Alice experiment, it's like 1/10 of what Alice consumes, because Alice uses normal magnets, which consume so much power. CERN, and now you asked me about CERN power consumption, it's around 220 megawatts, equivalent to the power consumption in Geneva Canton. Of course, we have the capability to go up to 300 megawatts, but this is the average, 220. And these days, since we have the shutdown, I think it's much less than that. The power is, I mean, we buy the power from the French grid, and mostly it's hydraulic power generated by the dams on the Rhone River. But of course, it's the grid, so if the dams are not working, it might be nuclear power.
Yeah. But also CERN is over time developing ways to make sure that we can be more green, and also use some of the energy from what we're doing, and the heat specifically, to heat homes in the local area, and just to reuse the energy in as much ways that we can. Just something that I want to say, because one big, not necessarily just at CERN, but in a lot of places, use of energy is computer farms and storing data. And one way that we get over this at CERN is that we store a lot of our data on magnetic tape. So we have a lot of data that we've collected over the years, and we want to have access to it. And so we store it on magnetic tape. So you can think like a VHS or these old storage systems, which means that if you want to access this data, then you have to actually ask a robot to go and get one of these cassettes for you and plug it in so that you can get the data. And then a lot of this data is also stored around the world, so not only just at CERN, but then it's also sent around on what we call the grid around the planet to different sites. So the UK has these set up so that the data is stored around the world. So that's not specifically about energy, but it's linked about, you know, we want to not have to cool computers all of the time to make sure that the data is available.
Wonderful. Well, thank you very much. I think that is about all we have time for the questions today. I know we had so many more hundreds of questions coming in. So apologies if we didn't get a chance to get round to yours, but thank you so very much for giving all the questions in. And thank you very, very much, Clara and Mohammed, for a really brilliant tour and for answering all of those very varied questions and for your time today. It's been, it's been really, really fascinating sort of walking around underground with you. And I know there was the odd sort of technical glitch here and there, but considering you're so far underground, I mean, what a spectacular opportunity to sort of have this tour with you today. So we really massively appreciate all of that. I think what we'll do now is we'll go straight over to the quiz and we'll get started on that, and then we'll have a wrap up at the end. So we'll see everyone's faces again at the end to say goodbye. But thank you very much, Clara and Mohammed. You've been absolutely superb. So what we'll do now is we will move on to the quiz. And for this quiz, so you have a chance to win an Atlas and CERN goodie bag. So if I share my screen. Okay, so the quiz today, so hopefully I'll give that a few seconds just to come through, and hopefully someone that I can see in my panel can give me the thumbs up to say that they can see that, see the screen being shared. I know that YouTube is about 20 seconds delayed. So Connie, can you give me a thumbs up if you can see the screen okay? It's funny, I can't see your thumb because you disappeared, but yeah, I think that was yeah.
It's all good.
Okay, super, super. So our quiz is being run through Mentimeter today. So for those who maybe aren't familiar with Mentimeter, it's really simple. You just need to grab your phone, your tablet, your laptop, basically any device that connects to the internet. And in your web browser, if you navigate to menti.com, there's an 8-digit number at the top of my screen. I think it should be 85323477. And so once you enter that, you'll then be taken into the quiz, and you should see the lovely Atlas logo with the welcome, the quiz is about to start on it. So if at any point you lose connection to the quiz, these details are going to stay up throughout. So you should just be able to follow the same steps and you'll be able to rejoin. So a quick note, again, just to those watching on YouTube Live, there is a 20-second delay between what I say and what you see. So please, from this point, as soon as you connect, please follow on your device and don't go off what you hear me say because there'll be a delay. So your device will be in real time. And if it gets confusing, just put me on mute. Just follow what your device tells you to do. So while you're all connecting, I will run through what you should expect. So hopefully this is updating now on your devices and you can see the next screen. So we have 15 questions for you today, and the winner will get to receive a brilliant Atlas and CERN goodie bag. So you'll get points for a correct answer, and you'll get bonus points for faster correct answers. So you want to try and answer quickly, but you also must be correct. Each question has 2 countdown timers. So one indicates the time you have to read the question, and the other is the time you have to answer the question. Now, it might look slightly different whether you're using a laptop compared to using your mobile phone. I've given some examples of what your screens might look like in this picture. But just be aware that there will be 2 timers. So when the question first appears, the first counter will start automatically. I'll also read the question aloud, then some multiple choice answers will come up and you'll have 30 seconds to answer them. So the first few questions will be related to the video that we shared when we were advertising this event that Connie mentioned right back at the beginning of this event. So hopefully you've all been able to watch that. And then we're going to move into some questions that are more related to the tour that we've just been on. And at the end, you'll get to see the leaderboard, and we will ask the winner to give their email address so we can arrange for their prize to be sent out. So I hope all that's clear, and I hope that's given everyone plenty of time to join. But as I said, the connection details will be visible throughout. So we'll start off with the first question, loads and loads. So we've got around about 75 people, it looks like, have joined, and possibly more throughout. Possibly there are more you've sort of grouped together on the end to figure out this quiz together. So absolutely perfect. So let's go first question. So the timer will start shortly. So what does the word atomos mean? Is it the smallest, divisible, indivisible, or atmosphere? Make sure you're looking at your phones when you're answering these. So the scores are absolutely racing in. We've got well over 180 people have voted. Perfect, let's see the answer. It was indeed indivisible. So well done to everyone that got that correct. Moving on to question 2. What are protons made up of? Is it neutrons, quarks, muons, or mangoes? Just a few seconds left on this question. Brilliant, 196 went for the correct answer, that was quarks. So we'll move swiftly on to the third question. And just remember, if you are on YouTube, obviously focus more on your device than me. So the third question, how many pictures does Atlas take every second? Is it 10 million, 20 million, 30 million, or 40 million? Some people are very quick off the mark. We've already had nearly 200 answers come in now. We've got 10 seconds left to get your answer in. Okay, so that's right, 90 people went for 40 million as the correct answer there. So very well done. Moving on to question 4. In the video, what do the physicists talk about at lunch? Is it free diving, politics, football, or physics? So it'll be a good test to see how many of you watched the video before you joined the tour today. So just 5 seconds left. Brilliant. So the majority, of course, went for free diving, which is the correct answer. So very well done to all those that were paying attention. So moving on then to question 5. How big is the Atlas experiment? Is it 2 double-decker buses, 2 stories high, 8 stories high, or it can fit on a penny? Slightly trickier question here. So we've got just about 5 seconds left now to answer this question. That's right, majority have gone for the correct answer, which is 8 stories high. Perfect. So let's move on to the next question. So question 6. How many bananas would you have to eat to receive an immediate fatal dose of radiation? Is it 10,000, 1 million, 10 million, or 10 billion? It's a slightly left field question, but hopefully for anyone who watched the video will maybe remember this as quite an interesting fact that they brought up. It's just 5 seconds left. Okay, so the majority have gone for 10 million, which is exactly right. So slightly closer this question in the answers, but well done to everyone that got that right. Moving on then to question 7. So we're nearly halfway through the quiz. How much data did the experiments at the LHC CERN produce in 2018? Is it 88,000 terabytes, 88,000 gigabytes, 88 megabytes, or 8 kilobytes? Some people very quick off the mark here, determined to go for those bonus points for speed. Perfect. So let's see. Yep, vast majority of people have gone for the correct answer, which is 88,000 terabytes. So congratulations. So now moving over the halfway mark now on to question 8. What new particle was discovered at CERN in 2012? Was it the top quark, the Higgs boson, the W boson, or the electron? Numbers going up very quickly for this question. So hopefully that's a good sign that everyone was paying attention to Clara and Mohammed during their tour. Brilliant. And what a relief. Vast majority of people have gone for the correct answer, which is the Higgs boson. So very good. Well done for getting that correct. Moving swiftly on to our next question, question 9. How long is the LHC in kilometers? Is it 16, 21, 27, or 32 kilometers? I thought this would be quite a difficult question, this one. There's lots of numbers to remember, but it seems that we've had a lot of responses come in very quickly. So maybe it's just me. And the vast majority again going for the correct answer, which is 27 kilometers. It's very well done. Moving on then to question 10. So we're into the final few questions now. Which of these is not a large detector on the LHC? Is it Atlas, CMS, Zeus, or Alice? We've had lots of instruments that we've been discussing today during the tour. So let's see if anyone can remember which of these is not the correct one for being one of the large detectors. And thankfully, again, we've got the majority going for the correct answer, which is Zeus. So yeah, really good. I think really this is going to come down to all about timing and who can get in there quickly with the correct answer. So moving on swiftly then to question 11. What is the highest energy that the LHC has collided at in TeV? Is it 7, 8, 13 or 14 tera electron volts? Just a few more seconds. And then we're down to the final few questions. And again, majority going for the correct answer, which is 13 TeV, which is great. It seems that you've all been paying very good attention to our speakers today. Moving on then to
stuff there, Chantal, don't they? I didn't expect.
So question 12. How cold do the superconducting magnets get in degrees Celsius? So I think we had this number mentioned a few times during the tour. So let's see if you can remember that number that I think Mohammed brought up a few times. Very good. So we've got, interesting. I think I've marked the wrong one here. So we might have to discount this question. I think, Mohammed, is that correct that we've got the wrong one has come up as being the correct answer? So we've got an error in the quiz. I'm sorry about that. Bound to happen with all these questions. So we'll discount this question and we'll move on to the next one. So question 13. What is the global network of computers where data from the LHC store is called? The mesh, the lattice, the matrix, or the grid? Absolutely right. Indeed, the grid. And then on to question 14. So just the last two questions now. Over 1 billion particle interactions take place in Atlas every, is it second, minute, hour, or day? Just a few more seconds to get in for this second to last question. Correct, it is indeed every second. So then the last question that follows on from that, your last chance to get a few more points in. Out of these interactions, how many get flagged as potentially interesting? Is it 1 in 100,000? Is it 1 in a million? Is it 1 in a billion or 1 in a trillion? Last few seconds then to get in your answer for this last question before we head over to the leaderboard to see who has won. 1 in a million indeed is the correct answer. Perfect. So then heading to the leaderboard, we can see here that just hopping in there into first place as the fastest is Joshua. So yeah, big congratulations there to Joshua. And if I can ask the people that came first, second, and third, so Joshua, Puggy, and Nia Roberts. If I go into this next slide, I'll leave this up on your phones. It will stay there on your phones. If you enter in your name and your email address, then we can get in touch with the winner. And if we can't get in touch with the winner, we can go to the second or third place to make sure that we get you a goodie bag. So do enter that. Please rest assured that your details will not be put on the screen. They would just be privately provided to us so that we can get in touch with you and send you out your goodie bag. So do that, please. Any problems, do let us know. But I will now wrap up and get ready to hand back to Connie. So thank you very much, everyone, for joining our Prestige IOP event today. I want to say a huge thank you to our host, Clara Mohammed, over at CERN, for taking us on an inspirational trip underground at CERN. And thank you to Miranda, Anna, Vince, and Elizabeth as well for supporting behind the scenes, helping to get this event organised and helping with all those questions that have just been absolutely swamping us. Thank you very much to Stephen for providing brilliant BSL interpretation for us at today's event. And of course, a huge, huge thank you to Connie for helping us to put this event together. It's been an absolute pleasure. And I would like to finally hand back to you, Connie, for some closing comments.
Thank you, Chantal. This has been fascinating. Learn, what a fun way to learn. Thanks again, Clara Mohammed. When you get back up above ground, I think I owe you a coffee. If you'd like to know more about physics in a fun environment, one of our music festivals, a science pavilion, is the WOMAD Festival in the UK, and it will be going live. That is with real bodies, end of July. Tickets are going fast, I've been told. But we have a great 3-day program on offer in the WOMAD World of Physics. You can maybe see that as my backdrop. When we were still Science Pavilion, we got promoted to the World of Physics in 2019. And we've been doing music festival since 2016 in collaboration with the wonderful Miranda Addy. Maybe see you there. Feel free to follow Clara and I on Twitter, Instagram, and the IOP Southwest Twitter as well for lots more fun science communication. Thank you, everybody, and for giving us this opportunity to collaborate with you. Maybe have a nice weekend.
Thanks, everyone. Bye.
Bye-bye.